Okay, so recording also has started. Only about 7 of you are there. But let me just refresh what we have already learned in the last class. We are slowly getting into the details of files, processes. So those are the things what we are learning. Uh, Last class we have written this particular program about how to create a pipe and also how to create a process and how to communicate between the parent and the child process by using the pipe. One end of the pipe is available to the parent, other end of the pipe is available to the child. Whatever is written by the parent on one end of the pipe can be read by the child process. That is how we have written the code, very simple line. So this is the actual program what we wrote. We need to include all the header files required, then the main function. To use the pipe this thing, we require an array of integers that can hold two numbers. One number is meant for file descriptor to write something, and another number is meant for file descriptor to read the data from the pipe. So int p of 2. Variable name can be anything. And then some variables we have declared meant for creating the process and capturing the process ID of the child and other written values and all that. So message that we try to write onto the pipe is this particular constant. Hello line 1, line 2, line 3, that kind of stuff. Then how to create a pipe is simple, straightforward. Pipe of the array, whatever array that we already have it, you are passing on that particular thing as a parameter to the pipe system call. At the end of this, like P of 0 and P of 1 are initialized with file descriptors of the corresponding pipe. So we are also trying to print them just to know. Most of the time, the numbers are likely to be 3 and 4 because 0, 1 and 2 are already opened with every process, in fact, meant for standard input, standard output, and standard error. Always the open system calls or pipe and all that, they return file descriptors that are next available, that are available in the next numbers in sequence actually. 0, 1, 2, and after that 3 is available, then 4 and all that. Actually, it's going to return the lowest possible value. Anyhow, so, and then you are actually trying to create a process here by using 4. And it is returning the process ID. And we also understood in the last class that parent process and the child process, or in other words, child process inherits all the file descriptors that are opened by the parent. So because parent before creating the child process has already created the pipe, so the pipe is available in both parent as well as child. That means pipe related file descriptors are available in both parent as well as child. So that is how we are actually able to communicate. Otherwise, parent will have its own memory space and child will have its own memory space. The only way that you can now communicate is between the file descriptors that are opened before creating the child process. So as usual, like whenever you are creating a child process, we use the simple pattern like switch pattern, switch off. So whenever it is 0, it is a child process, -1, an error occurred while creating the process, so you are not doing anything, and then anything other than that is a child, parent process. So parent is waiting here and then writing the message onto P of 1. P of 1 is the actual writing end of the pipe. Read end of the pipe is P of 0. So like you are actually, so what is happening here? So you are writing, you are trying to read from the pipe in the child process. You are trying to write onto the pipe in the parent process. This is what we have learned, right? So, any improvement in the attendance? Let me just see. So, about 11 students are there. Okay. So, slowly we'll move on to the today's next discussion point. Apart from this, now, like we are trying to go into uh, like the program that we would like to continue is the following: how to use the duplicating the file descriptors. Net was interrupted. There is some issue there. I think we are back to this. And now we are actually talking about this particular system called a dupe system call. Duplicate a file descriptor. There are three different versions of which we are going to try with the two, dupe and dupe 2.
Sir?
Sir, voice is not audible, sir.
Okay, I think now everything must be all right. Are you getting my voice?
Yes, sir.
Okay. So there is some disturbance in the line. All right. So this is what we are actually talking about, the dupe system call. We are trying to understand in today's class by using the like C programming and all that. That is the idea behind. And what dupe will do, you can see here the signature of that dupe, like int dupe of int old FD. So given an existing old file descriptor, it returns another new file descriptor which will have the same features, which will have the same functionality. So in the case of the dupe 2, you ask for like a duplicate of an existing one with a number of your choice, with a file descriptor number of your choice. So that like you want to use in that particular context. So like for that, you can see here the explanation part. The dupe system call creates a copy of the file descriptor using the lowest numbered unused file descriptor for the new descriptor. So after a successful return, the old and new file descriptors may be used interchangeably. Both can be used for the same purpose. Dupe 2, in the case of that, you are going to give the new file descriptor also. And in case the new one is already in use, it's going to silently close before being reused. That is the idea here. Now let us actually take a look at the program that we will be writing and then understand how things work and all that. Okay, so here the like there is no pipe and all that. You don't require this particular thing. We can safely close this particular thing, and you are not using any of the other things in fact. So for the time being, if we want, we can do in this particular manner. So how do you use it? Dupe to off. Like we are trying to use the dupe to system call, for example, dupe to off. What are we doing? We know that already. Like three file descriptors are going to come with every process: 0, 1, and 2. The file descriptor 0 you get, it is used for reading the data from the standard input. One is meant for writing something onto standard output. Most of the time it's going to be the screen. Two is meant for writing some error messages, that kind of thing. So he is going to, again by default, will be written onto the screen, standard error. So now what we are trying to do is dupe 2 of, you are saying 2 comma 1. What is the meaning of this? So file descriptor number 2 is also now available on number 1. So at the end of this, what happens? Whatever that you write either onto 1 file descriptor or onto 2 file descriptor will go on to 2 itself. So initially, first let me show you the other example, and after that we'll come to the other part of it. So what you do is I think I wanted to show you everything. First, maybe this entire clutter also I will remove so that the program becomes simpler one, and after that we can actually show you what we are actually trying to do that. I'm just making very simple for you to understand. All this is going to be removed. So right now there is no dupe or nothing like that. What you are actually doing is this particular code, let us say. So what are you doing here? Write off. Write is a system call by which you can write onto any file whose file descriptors are with you. So we already know that 1 and 2 are already open for every process. So 1 is meant for standard output, 2 is meant for standard error. Now what are we doing here in this case? Write off 1 comma, that means on to file descriptor 1, that means it's the normal output, standard output. So this is the message to be written, and how many characters are there are counted, and that is 23. 23 characters are there in this. So similarly, you are writing on to file descriptor number 2, which is error actually, error output. So error output and all that. 22 characters are there because there is one less than that, and then you are terminating, right? So this is a small program. Let us see. So and then you compile it. This is the compilation this thing, right? It is compiled now. So when you run this, this is how you can run it. You get naturally normal output on every one, error output on every two. The entire thing comes onto this because you are not using any redirections right now. So for every process, you have 0, 1, 2. And whatever is written onto 1 is also coming to the screen. Whatever is written onto 2 is also coming to the screen. Up to this, no issue. So there is hardly anything. But the question is, when you now try to redirect, right? When you try to redirect, what are you redirecting? You are redirecting the standard output because of this normal greater than. Either you can say simple greater than or even 1 greater than also. Both are one and the same. So whatever is written onto file descriptor 1 while running this program, whatever is written onto that is now redirected to this particular file, special file called device null. Anything you write onto device null is like synced, like nothing is going to be written anywhere as such. So when you do like this, now anything that is written onto file descriptor 1 is gone to the device null, whereas the other thing, error output and all that is coming onto the screen itself, because the error channel is still mapped to the this particular screen as a part of it. Similarly, you can also in fact say, for example, you redirect the standard error, then naturally you get the normal output onto the screen. Or you can redirect both. So you understand now what is going on here. So whatever is written onto 1 is different, whatever is written onto 2 is different, right? So most of the time, understand that like error messages are written onto file descriptor 2, and the normal output, useful output is written onto 1. Like so, that's the protocol that many of time like we will be following. Now, so we know that 1 is different, 2 is different, but you want now both 1 and 2 to go to the same output, right? That is the idea, right? So whenever you use dupe system call, so you say dupe 2 off, whatever is written on to 1, right, should also go on to 2, let us say, right? It can be either way, you can always say. That means now, so right now 1 is there, 1 is working, 1 is being written onto standard output, 2 is written onto standard error. But now when you say dupe 2 of 1 comma 2, 2 is no longer there. In case 2 is already there, 2 will be closed. And then 2 is now available as if with the functionality of 1. That means at the end of this, whatever you write onto 1 or onto 2 is available on 1 itself. Is available on 1 itself at the end of this. That means only the normal output only you will see. Even when you are writing by using 2, that also will come to the normal output. That you need to understand. So at the end of that, 1 is available on 1 only, 2 also is available with the same functionality of 1 as a part of it. Now you just simply save it and then compile this particular thing. Compile this, right? We have done that. And then you run this without any redirection, you will naturally see the output will be same. Both the lines you will actually see, right? Without any redirections. But when you use the redirection, for example, so greater than /dev /null. See, that means because as we know in the program here, 1 is available as it is, 2 also is available on 1 only. So 2 output also is going into the 1 only. So because of which, when you redirect the normal output to device null, both the lines have gone there, in fact. Whereas if you redirect here only the channel number 2, only the channel number 2, see, so number 2 here is different, like so. So it's going, 2 is going on to the null there, whereas the output, if you see, right? So both the lines you are getting onto that. So that means whatever is being written onto 1 is written is available on both the things as a part of it. So depending upon your situation, you can always go for the duplicate of that and so on. This will be used while using the pipe and all that. Pipe combination with do will help you to create that kind of a command pipe command structure, which will come to that a little later. But the do piece, the purpose of the do piece, exactly this particular this thing. I'll show you one more thing, uh, what has been there. Like by default, as you know, 0, 1, 2, they are available. In case you close it, you close one of the file descriptor, close 0. That means your standard input you are closing. But after closing the standard input, you try to put, for example, you have a message anyhow, no issue, printf enter a number kind of it. And then you try to perform scanf. Right? You perform, you try to read something. %d, comma. Some variable you require naturally, ampersand, address of some let us say. Address of N you need to declare naturally. Like this. So once you read this, so you can say printf square of so and so number is another number. Then you write, comma, number n, and its square is n into n. N into n. Here essentially that f is required. So square of so and so is so and so, n comma this particular. So what are you doing here? If you don't close it anyhow, so here, for example, so this let me make it as like a comment, right? Let me make it as a comment. Right. So this is a comment. This thing. So the other lines are there. So when you run this particular program, you compile this, and then you run this particular program. So run it. So it will wait there anyhow. So you give 5 here. Square of 5 is 25. No issue. This is straightforward, right? All of you are familiar. Scanf by default is trying to read from the standard input. But what if you actually close the standard input, right? And then try to use skill scanf there, right? So that's the question. So now you are trying to close the 0. You're closing the file descriptor 0. You're closing the standard input. And still you have scanf there and all that. So what is going to happen there? You need to take a look into that. Initialize this with some value so that like this, and then now compile this particular, right? And then run the program. So if you run it now, if you see here, it's not waiting. It's not waiting for the user to enter the data. So that's why it's saying square of 0 is 0, because your scanf is no longer meaningful because the file descriptor 0 is closed. So scanf is trying to read from the standard input. Standard input itself is not there. So that's the reason why this has got 0 effect, right? So you need to understand the meaning of these things. Once you close a file descriptor, then you try to still use it nothing is going to happen there as a part of it. It's not giving any error message, but not even runtime error also you are not getting. But scanf is not waiting at all there. It's just going through. And n is 0, that's why the output is so and so. So slowly get used to these things. This is one case. So, but in case like other things, as usual. Like so, this is how one can use the dupe to and all that particular entities. Anyhow, so let's now take on to the final program, which we call it as a pipe related thing, right? How to implement that and so on is a slightly involved one. Let us actually go into that pipe IPC mechanism. So this is the actual thing. This is the actual thing what we have learned in the last class. But let us make it more robust, whereby the actual pipe symbol, actual pipe, as given in the what it is in this particular scenario. What is going to happen when you issue a command one, ls followed by a pipe symbol and then a word count as a part of it. So what is happening? The output, standard output of ls becomes the standard input for WC. So how are you going to make that to happen? Right? Standard output of one this thing should be available as standard input for the other. So whatever is the input that is there should no longer be there, but that should be attached to the one end of the pipe. See, between ls and ls is one program, WC is another program. The standard output, now actually what are you doing here? You are creating a pipe actually. You are creating a pipe that has got two ends, of which writing end of the pipe is a duplicate of writing end of the pipe is a duplicate of standard output of ls. That is how things are happening actually. Whatever is the standard output that is being written by ls is now duplicated to one end of the pipe. So that's the reason why ls is, strictly speaking, ls is not modified. ls is still writing on to the standard output only. But because that standard output is a duplicate of that pipe, so ls output is going onto the pipe actually, onto one end of the pipe. Similarly, WC is standard input is not changed, but so it is now made to be a duplicate of the input end of the pipe. So WC is actually reading from the input end of the pipe. ls is writing to the output end of the pipe because of the duplicate file descriptor concept. Duplicate file descriptor concept. So that is what we'll have to implement in case we want to here as a part of that. So for example, here this is one example, IPC, pipe IPC and all that. Probably we can just simply have save as, I will say, IPC 2 kind of thing, two programs we are going to have it, IPC 2, let me, IPC 2. So we are now going to modify this particular thing with slightly different purposes and all that. So let us see what's going to happen. So far no issue, like how to create a pipe, you know it, and then you are doing a fork, so at the end of which you have got a process, child process. And then this is there, child process is there, this is the parent process. Now we will also use a kind of a duplicate kind of thing, right? So what are you going to do in the duplicate kind of thing? So let us look into that. So what we are going to perform. Fork is there, like no issue. So what we will do is child will read from the standard input and parent will write onto standard output. So we want to now have duplicate of these things. So we will say duplicate of dup2 of what is to be done in the child process. So standard input of the child process but rather what it is, the reading end of the child, reading end of the pipe, reading end of the pipe. What is the reading end of the pipe? Reading end of the pipe is P of 0. P of 0 must also be available on standard input 0. If you do like this, so what is the meaning of this? You just try to understand. Do 2 of P of 0 comma 0 means, so reading from the pipe, right, you can do by using from P of 0. Whatever is the effect of P of 0, you are going to get the same effect on 0 also. Same effect on 0 also. In the following lines, if you try to read from 0, it is as if you are reading from the pipe end. You are reading from the pipe. So all your normal programs, they are designed such that they read by default from standard input. So they are reading from the standard input is equivalent to reading from the pipe actually. Reading from the pipe here. So that is what is going to happen here. So it's going to read from the pipe. So in the child now, instead of running the same old program, we will be running a different program now altogether. So let us do that particular scenario of loading the other programs. Now you are not going to read here. You are not reading the data on your own, right? Remember that. But what you are actually about to do is very interesting thing. You want to run a different program on this, and that program you can actually run by using exec system call, exec L or exec V, either one of them. So let us actually run this by using exec L of. So the exec this thing, what are the things that you require, parameters and all that, you can easily see. The other day we have seen it's a loader. It's going to load exec L. So it's available on the third this thing, no issue. Exec L of what is to be provided? First, it is a path. That means the path of the command to be executed, the complete path. Whereas the advantage of using exec P is that you don't have to use the complete path. You can give only the file name or the command name. So we will be using exec LP so that it becomes easy. You don't have to give the complete path. Or in case we want to, we can always do that way also. Okay, let us start with exec L and after that the other one. Okay, so after the path, then the command line arguments you will have to give. At the end of that, you have to terminate that with null value. You have to terminate with null value. So let us now come back to this particular thing, exec L long. So we will count here how many, like we'll perform the word count on this particular data. Hello, line 1, line 2, line 3, word count on that. So that's the reason why you are going to run the word count program here. And its corresponding path is /bin/word count. You are now running this particular program. Child is going to run a different program after forking a process. So, and then what it is, the list of all those things. The first one command line argument, like the 0th command line argument is word count itself. Most of the time, it's the same WC you are going to keep. And then the options, right? Options, nothing, let us say, which is going to give you all the details about, but you have to terminate with null. So you have to terminate with null, meaning that, so you specify star 0. That is the terminating semicolon. So what is happening now? So even this message also, this also you don't require, because like what you are actually doing is that you are creating a duplicate of P of 0 to be available on 0 itself. Now this WC program which you are going to run by default tries to read from standard input. So it is reading from 0 is equivalent to reading from P of 0. By default, all your filters, they read from standard inputs. So they try to read from 0 and 0 is now mapped to piping one end of the reading end of the pipe. So because of this do2 symbol. So anything that is written onto the pipe is now available to this particular program. So here, this sleep 2, you can always have it, no problem, and write it onto right end of the pipe. So let us now see, so what is going to happen as a part of this. We have to do several other things normally in the textbooks and other programs and all that, but I am now trying a minimal version. So you have duplicated that particular thing and then doing all that. Here, this is actually you are straight away writing it over to P of 1. Let us see what is going to happen. And then after that, we'll see. So this is IPC2 dot C. That's what we'll have to compile. Uh, pipe hyphen. Somewhere. I see. So save it. Come back to this particular thing. Pipe hyphen IPC2. IPC hyphen. Okay, so minus O. Then again, all that. Two is gone. So it's compiled, no issue. So clear the screen. Then you want to run this particular program. So dot slash this particular. What's going to happen now? What is our interest? Whenever you run this, so this is going to create a pipe, and this is also creating a process. And then running the child, as a part of the child process, it's going to run the WC program. And in the parent process, you are writing this particular message. Whatever you are writing here on one end of the pipe is read by WC program. And that is going to give you a count of like statistics of all those listings. So that is what is expected here. So when you run this particular thing, find descriptor numbers 3 and 4, nothing, you are not getting anything here, 3 and 4. So where is that? So this is there, 3 and 4 is okay, P of 0 and all that. You are creating this particular thing, but we have not got any output and all that. 0 is there, exec L and all that. P of 0 and all that. Loop 2 of all that. We can actually close some of them normally. Let me close off. So 0 is there, standard input. So whatever is there on that particular thing, for the pipe, so you can say close of P of 1. Close the one end of that. Whereas here, so that's a pipe. So here, let us say close. The parent is only writing onto that, whereas reading end he is not going to do anything. So reading end can be closed here. Reading end can be closed. P of 0. No issue. So these two you are performing. There 0 is there as it is. Here you are writing onto P of 1. Let's now examine what's going to happen at the end of this particular thing. Compile it. And now run this particular thing. So even now we are not getting anything. But let me remove this also probably. Writing end of the pipe is P of 1. And message is there. Message is there very much. strlen of all that. Exec L followed by WC, WC, and then is that particular thing. Other arguments, nothing is there. Okay, exec L off. So any header files to be, that's not the issue. Pipe hyphen IPC2. So we are not getting any output here. I'm actually expecting the output of the WC to be there as a part of it. Exec L off. Let me give some more options here. Minus number of lines, whatever. Star followed by 0 is okay. Exec L and all that. Case 0, 4, RV, pipe of P. P is there, RV is there, no issue. Loop 2 of P of 0, comma 1. P is there. P of 0 is also available as 0. So anything you perform on 0 is effect of P of 0 only. Close P of 1, exec L and all that. Okay. File description numbers 3 and 4. Loop 2 of P of 0. P is there. This is correct only. What's going on? 0. P of 0 closes the pipe itself will be closed. That's of no use. 0 is available through this particular. No. Close of P of 1. Close of P of 0. Could writing on to P of 1. It should happen. Better to have like this only. So I'm just expecting the output here actually. Exec L, bin WC followed by WC hyphen L and all that. Let us examine the return value of this. Is there any this thing? Let us see where the bin is. Slash bin only it should be. Where the WC is. Which one? Word count. User bin. Oh, that's the problem. So actually, it's there in user bin. So Maybe that should be the problem here. Path is wrongly given. Slash user bin, this thing. And then close this, do on anything that is available. P of 0 is also available there. I think that should be most likely the case scenario. Close all that. So now let us see like what is going to happen. Because we are not using the return value of that, probably it is just failed there as a part of that. Right. So now you are actually getting there, as you can see. So, that's the actual mistake. Everything else is all right. So you have to specify the complete path, and it so happened that it's there in user bin. So what we will do is now, even this can be removed, not required. So meaning that you are running the WC with no options. So you are going to get all the things there as a part of it. So dupe 2, you are closing the one end. I think even if you don't close also, most likely we should get. That's what I wanted to try actually. But somehow, let us say, you're not doing anything. So you are just simply getting a duplicate of reading end of the pipe onto the standard input and then going on it. And here you are doing in this particular manner. It may not be a good practice, but this is a bare minimum program. So let us see like what is going to happen, and after that we will come to that. So you compile this and again run this particular thing. So 5-digit numbers 3 and 4, you are not actually getting in this particular manner. So we are not getting any output there. But it so happened like probably if you may have to close the one end of the pipe. Let us see here. So is it mandatory there? Is the scenario situation close? Reading end we are using, but writing end you are not required. So you are closing the other end of the pipe. So similarly in the parent is only writing, but it is not going to read. So reading end of that can be closed. Close of P of reading end. Reading end is P of 0. And then you are writing onto P of 1, which is becoming available on P of 0 as a part of it. So when you save it and you again compile it, now you run this, you can see. So you are getting the output now. There are 3 lines, 7 words, and 28 characters. This is the output of the like your child program, what you are actually running. See here. So this fellow like WC is getting the data from the standard input, and because standard input is redirected by using dupe 2, it is getting through the pipe. So whatever is written here is available there as a part of that. So that's the beauty of it. Like, so you have to close the unused ends of the pipe in the parent and the child. If the child is trying to read from the pipe, so let the child actually close the other end. So that way you are able to establish the connection between both the things. You can run any program now here. For example, you want to run something like, let us say, the other way you want to see. So let us run a different program here. Of that can be captured here. The output of that can be captured here. In which case we will have to use the read operation and all that particular thing. So either way we can always do that. But to make things simpler here, let us say what are the other possible filters that we can use. WC is one thing. So we can look for, let us say, grep in fact. You want to grep for something, right? So where is grep available? Like we'll have to actually take a look into that. The other easier way is, see here, instead of exec L, you use exec LP. Use exec LP. In which case you don't have to give the complete path. You can just simply give like this. Then it uses the path and then catches wherever it is available. Exec LP, right? In which case it uses the path and searches in every directory within the path environment variable for this particular thing. So that is the advantage of using the LP kind of it. You don't have to know where it is. You don't have to give the complete path of that particular thing. So you can see here, it's also now running 37 and 28 without having any issue. Now instead of running WC, you can as well run grep also. This is only, this name can be anything. This has nothing to do. It is only, this is the one that is actually doing the job. This is only command line arguments. Zeroth command line argument, how it should be interpreted. That is the idea behind this particular this thing. So most of the time, it's going to be the same as that of this particular thing. So grep here. And now after grep, what is to be done? You'll have to specify, right? You have to specify the pattern, and that pattern can be specified here. So what is that you want to search for? Let us say 2. You want to search for the character 2 as a part of it. So now like this grep is receiving the data written by our parent process. What is the data that is coming to that? It's getting hello line 1, hello line 1 new line, line 2 new line, line 3 new line, like that. So when you are searching for grep 2, only those lines that match the 2 is going to come, right? So you can now see, save it, then come back to this particular thing, and then again recompile. Now you run this binary file standard input matches. What is this thing? Standard input matches. Something special is there. Grep is there. Exec LP of grep comma 2 P of 1. We have not done anything, right? So we should get actually line 2 is the expected message. What we are actually expecting. Great. Close. We'll do one thing. We'll close this end so that it's going to be more accurate actually. We'll close the one end of the file. Normally it should have happened even for the word count also. That may not be the reason, but still you are going to close. After writing P of 1, you close this particular thing. P of 1 also. So when you close one end of the pipe, the other end will get to know, and then it is supposed to complete it. Exec LP of grep followed by all that. Let us see like what is going to happen. So all of you are there, okay. So here we are basically closing that. Let us save it. Go back to this. Compile. Type IPC2. IPC2. Binary file standard input matches. Okay. So somehow standard input matches. What is this error message? Character hello line 1, line 2, and all that crap. Do 2 of P of 0, comma 0. 0. Grep is going to read from 0. In the 0, you have the same data. Somehow it should not. No such file or directory. Oh. Grep followed by Oh, we are using the syntax a little bit wrong, probably. Okay. What is happening? Grep is issuing the message. Grep caller. Oh. Exec LP. What is the syntax of the grep? You can see man followed by grep. So grep options are optional. The pattern and file also is optional in fact. That's what we are actually trying. Grep followed by just simply give a pattern so that it takes the data from the standard input. So it should be okay there, like pattern followed by the file. So here it is actually thinking as if this is the this thing. Somehow it is not actually matching my idea. Exec LP of WC. For WC, oh, okay, sorry. Actually, so earlier one, we are actually giving WC is what you are trying to run. And then 2 is the file name. Naturally, it's a wrong thing, right? So this is understandable. Sorry. Like this, you'll have to give. Here, this name can be anything. It doesn't actually tell you anything. That means whatever name that you give, that is what it is echoing back. That's why even though you are running WC, but it is saying grep, it's actually running WC there. Okay, so this is, let me just give you in this particular fashion. Okay, like this. Now you run. So you are getting properly only. Word count program is loading properly. Grep is what is happening over there. So the grep is a question mark somehow. It is there in bin grep basically. So grep somehow is not working as expected. Let me just give exec L with the complete path as like this. Bin grep, and then grep is there. Then it should actually look for the pattern. Grep followed by pattern here is going to be here. You have to give the pattern. Pattern is 2. You want to look for 2 there as a part of that. And char star and all that. It should actually work. Let us see here. So binary file standard input matters. Somehow it is behaving something wrongly. But let's try a different one. Instead of grep, let us try something else and then see how things are going to actually work. Some other filter. That's what we are actually going to try. For example, translate TR. Let us use TR. TR. So TR, what is the syntax as we know? TR syntax is, so for example, whatever output that you give, so you can give, for example, echo some A, B, C, and then you pipe it to TR, and what? So you have to specify A to Z, right? A hyphen Z. Normally we give, this is the easiest one. A to Z must be converted to capital A to capital Z. Then it gives in this particular manner. That means you have to specify TR, and then one of the arguments must be A to Z, the other argument must be capital A to capital Z. So we have to specify that particular thing. So here, let us say A hyphen Z is one parameter. This is one argument here, what you are actually giving. The second argument is capital E hyphen capital Z, like this. So all the parameters, basically, you are running the TR, and these optional or command line arguments are A to Z, and ultimately it should be terminated by this particular thing called char star 0, right? So it should be ultimately terminated as such. No issue. So this is what we are trying to. Now let us see what is going to happen. You see here, you are getting actually hello line 1, line 2, line 3. So everything fine. Only for grep somehow, grep is it's really puzzling me. You can even use sort and all that also if you want. For example, right? You can try here sort. You can try here SORT sort, and here also sort only. And what are the options here? Probably you want to sort in the reverse order. Let us say you want to sort on the reverse order minus R. Minus R. And then the other things, nothing as such. Right. Sort minus R, and sort is going to get its data from standard input. And that is being written here, right? So the same lines there and all that you are going to actually get it. So you save it and you compile and you run this. See there, line 3 is the line 2 and then hello line 1, right? It is in the sorting that data in the reverse order. Anyhow, so this is an example of the usage of the do system call as well as creating the process, inter-process communication. So essentially, like whatever is being written here by the parent is available as input for the child. So using the standard input kind of thing, grep, I will look into that. I will give the clarification in the next class. It should not be saved that way. Like somehow it's probably there is some issue there, which I will try to find out and give the clarification in the next class rather. So this is about the processes and all that. What is left out now is the signals by which you can send a signal there and all that to interrupt the process and all that. Then the other one is the locking. You want to lock the files, file locking kind of thing. I think with that we come to reasonably one level of what you call all that. So this exec anyhow, I think you should be able to go through the corresponding notes on exec. About there are different variations. Exec V is there, vector by which you can pass it on there and all that. So it's very well given in some of the books like I will show you which book you can just follow the syntax part of it and all that. Introduction to Java and all that, Unix network programming around Robert Love, Stevens, Stones. This beginning Linux programming, 4th edition, Matthew Stones is a good book for most of these system programming examples and all that, right? This particular book, I don't know whether I have shared it or not. I think I must have shared this particular book also, Stone's book. Let us see here, books section. So it's there, this 4th edition. This is the book. If you want, we can also open that and show you all that. So here I will show you the syntax details of that particular thing. Right. So these are the different versions of those things. Exec L, exec LP, exec LE, exec V, VP, VE. One example we have seen here, and this is how you can use. This is how you can actually use it. You see, exec L off. So you can specify the PS program to be executed. Command line arguments are PS and AX. At the end, 0. I have only typecasted, and you can avoid that also, no issue. Same thing, exec LP off. You don't have to give the complete path, instead only the file name can be given. And then all this. Same thing by using the environment variable if you want to pass. Exec LE off, PS, AX 0. Up to this, it's actually arguments and all that. And at the end, you pass on the environment also. So environment and the command are created here, as you can see. Char star constant, right? Argument vector is equal to, you create an argument vector with the data being initialized like this. Similarly, environment variable is initialized in this particular fashion. And then you can use the exec v. Instead of list, you can use a vector. Exec v of /bin/ps. And to this, now you have to pass on the argument by way of a vector or an array. And that array name is specified here. PS underscore argv, which is already initialized here. This vector or array is initialized with PS, AX, and 0. Ultimately, it should be terminated by null character, null pointer as a part of it. So you can just follow this particular book and try to understand the other details. And some more programs are given here, right? So go through my explanation, and these books will help you to better understand the remaining things. So for system calls part and all that, go through this. For shell programming, this book is very good. Like what it is, maybe basic Linux commands with example. This book, shell programming. This book is very good as a part of it. So just go through that. That's it for today. And next week we will continue, especially the locking files, locking the files, and what else? Signals. So those two will have to continue. I'm just stopping the recording.